You're going to want to watch this video all the way through. Some of the best parts of it are right at the end. And it's another example of one of the things that drew me to mathematics in the first place, when I would find things that initially seemed unrelated and find out that they had a very close relationship. That's one of the things I still like about mathematics, and you're going to see that in this video. So here's a definition for what's called an iterated function. If x is in the domain of some function f, then the sequence below is the orbit of x for f. And the sequence is very simple. It's just like this. X, that's the number we're starting with. Then we find f of x, then f of x, f of x, so on and so forth. So visually, the difference is just a regular function like we're used to working with. If we drop x in, what comes out of the function is f of x. Well, if we start here and we drop x into an iterated function, what comes out is f of x, and then we take that f of x and we drop it back into the function. And then what comes out from that is f of x. Then we take that and drop it back into the function, and what comes out from that is going to be f of x. So what you get is a sequence of function values starting with the number x. First we get f of x, then f of x, so on and so forth. So each output becomes the next input. And then when that output comes out, it becomes the next input, so on and so forth. So that's kind of a visual picture of what these iterated functions do. Now I want to show you an example, but I'm going to have to move the board over a little bit, so I'll be right back. Okay, so here I want to find the orbit of x equal 1 for f of x is equal to 2x. So what I'm going to do is I'm going to start by dropping x equal 1 into the function, and then what comes out is going to be 2 times 1, or 2. And then I'll take that value, 2, and I'll drop it back into the function, and what's going to come out is 2 times that, which will be 4. And then I'll take that 4 and I'll drop it back into the function, and what will come out will be 2 times that, or 8, so on and so forth. So you can see the orbit of 1 for f of x equal 2x is going to look like this. 1, 2, 4, 8. The next one then would be 2 times that, or 16, 32, so on and so forth. It's very predictable, and once I see what the pattern is right here, I don't have to go back to the function value to see the next thing that comes out. I can just notice what this sequence looks like and keep adding on to that. So not all of them are quite that easy to see. I'm going to go to another board here and show you another one of these that's a little more complicated, but that we can still see that it becomes predictable. Let's go to the next board. Okay, here's our next orbit that we want to find, the orbit of 2 for f of x equal 1 plus 1 over x. So I've drawn a little function machine right here, and we're going to input values of x, and what we're going to get out is 1 plus 1 over x. So I'm going to start by inputting 2 in here, and what's going to come out of that is going to be 1 plus 1 over 2. Okay, and that's going to be 2 halves plus 1 half, so that's going to be 3 halves. That's my first output. That becomes the next input, so I'm going to take that and put it back in here. What's going to come out then is going to be 1 plus 1 over 3 halves, which is going to be 1 plus 2/3, right? And 1 plus 2/3, that's 3/3 plus 2/3. I'm going to end up with 5/3. That's my next output. Let's put that back in. And then what comes out from there is going to be 1 plus 1 over 5/3, which is going to be 1 plus 3/5. And then 5/5 plus 3/5 going to be 8/5. All right, so let's see what we have so far. As far as this orbit goes, it looks like I'm starting with 2, okay, which I can call 2 over 1 if I want, just to make it look like a fraction. My first output was 3 halves. My next output is 5/3. My next output is 8/5. So I can see this orbit starting to take place. You can kind of use your intuition and say, what's the next number going to be? Think about it for a little bit. I'll actually put this back in. Let's take 8/5. put it back into the function, see what comes out. 1 plus 1 over 8/5. 1 plus 5/8. Okay, 8/8 plus 5/8. 13/8. And then you can see that's the next number, and you can see they're consecutive ratios of consecutive members of the Fibonacci sequence. We saw this before with both the golden rectangle and also with our continued fraction that we had. So now that I see how this sequence is going with the Fibonacci numbers, I don't have to actually go back to this function machine to generate these numbers anymore. I know that the next one is going to be 21 over 13, so on and so forth like that. So this one becomes predictable also. Now it turns out with these iterated functions that the most interesting ones are the ones that are not predictable. And I can't really take a nice simple function and do that right here, but I'm going to take it to the next board and we're going to play what's called the chaos game so you can get a sort of intuitive feel for what these unpredictable iterated functions, what they behave like. So let's go to the next board and look at that. All right, here I have a nice equilateral triangle right here. I'm going to start this chaos game by picking any point whatsoever inside this triangle. It doesn't matter where we start whatsoever. Then I'm going to roll a die, and depending on what number comes up on the die, I'm going to move halfway to this vertex, or this vertex. So if I roll the die and it comes out to be a 1, I'm going to move halfway here and stop. Okay, then I'm going to roll the die again. So I just keep doing the same function rule over and over again, which is rolling the die and observing what number comes out. Okay, so I'll roll the die the first time. Okay, it comes out 2, so I'm going to start here and move halfway to that vertex and stop. Okay, here was my input. I rolled the die, I looked to see what it was, came out to be a 2, so I moved halfway to this vertex and stopped. That's my output. Now that output becomes the next input. So from here, I'm going to roll the die again. Okay, I'll do that. Okay, it comes out 4, so I'm going to move halfway to that vertex and stop. Okay, and that's my next output, which becomes the next input. So I roll the die again. Let's see, I'll do that. Okay, it comes out 1, so I'm going to move halfway back here and stop. That's my output for this input. And in between here, to know where I was going to go next, I had to roll that die and observe what number came out. So you see, I never know what's going to happen next. I need to always go back to that function rule, which is roll the die and observe the number that's there before I know what to do next. And each input becomes the next output. Okay, so here I am right here. Okay, let me roll the die again. Okay, it comes out to be 6, so I'm going to move halfway to this vertex and stop. Okay, so on and so forth. So if the next one came out 4, I would move halfway here and stop. Next one comes out 5, I'd move halfway here and stop. If the next one came out 1, I'd go halfway here and stop. But you can see it has that feel of an iterated function. We have one function rule that we apply over and over again. We start somewhere and then we get our first output. That becomes the next input. Apply the function rule. We get the next output, which becomes the next input. Apply the function rule again and again. But once I'm down here at this point, I don't know what's going to happen next until I go to that function rule. So it's completely unpredictable. Now what I'd like to do is take my graphing calculator and show you what this chaos game looks like when we do this over and over again very quickly. So I've programmed this into the graphing calculator. I want to show you what that looks like. So let me go get the graphing calculator. Okay, so I've got my graphing calculator here, and what I've done is I've programmed into it a random number generator that will generate a random number between 0 and 1. If it comes out between 0 and 0.333, I'm going to move halfway to this vertex. If it comes out between 0.333 and 0.6666, I'm going to move here. And if it comes out between 0.6666 and 1, I'm going to move halfway here. And then I've drawn a little equilateral triangle on the screen here, and so you're going to be able to see it move around. So it asked me what the first point's going to be, so I'm just going to put it right in the middle at 0.5 and 0.5. And then it's going to start playing that chaos game, but it's going to do it a lot more quickly than I can do it really here on the screen. So as you watch this, what you see is it really does look chaotic. I never know what's going to happen next. I've got to keep going back to that random number generator to generate a random number that tells me where to go next. Each input becomes the next output, and so I get a real chaotic sort of looking graph. Kind of looks the way things feel when your life's sort of out of control. You know, you just don't know what's going to happen next. There is some mathematics involved here. I could ask myself, is this a space-filling curve? Meaning, at some point, is it going to end up going over every point inside that equilateral triangle? So that's what it looks like. Pretty soon you're going to see it gets all filled in everywhere. It just keeps going in the same manner as that. So what I want to do next is go ahead and play this chaos game again, but this time I'm not going to draw in the line segments, I'm just going to draw in points. So let me erase this board and come right back. Okay, so again, here's my equilateral triangle. Okay, I can start anywhere in here that I want. Let's start with that point. I roll the die. Let's say it comes out 3. I'm going to move halfway to that vertex and stop. That would be my next, that would be my output. But I'm not going to draw the line segment in this time. So there I am at this output. Roll the die again, see what it comes out. Let's say it comes out 2. I move halfway to that vertex and stop. I get that point. Roll it again. Let's say it comes out 6. I'm going to move halfway to there and stop. Let's say it comes out 3, halfway there and stop, so on and so forth. You know, you see you're just going to get a sequence of points depending on what that die comes out, and they're going to just kind of be, they're going to happen sort of randomly because I'm using that rolling that die to see what they are. Again now, let's go to the graphing calculator and do the same program I just did, except it's going to do the points now instead of the line segments. Let's see what that looks like. Okay, so it's the same program in the graphing calculator here. It's just not going to draw the line segments. It's only going to draw in the points, but it's going to go through the same process, just like we're doing with the chaos game here. Okay, it asked me what point I want to put in first, so I'm just going to put in 0.5, 0.5, press enter, and it takes off. So you can see the little points starting to appear. They appear very randomly. Each input becomes the next output. I never know what's going to happen. It never becomes predictable, so I always have to go back to my function rule to find out what the next output is. Once I get that output, that becomes the next input. So this thing's just doing it very quickly, much quicker than I can do it on the board. So let's just watch for a second, see what happens. Okay, and so little by little, you see it starts to take shape, starts looking like the Sierpinski triangle, and in fact it is the Sierpinski triangle, that very regular deterministic process we use to get that Sierpinski triangle also comes out of this chaos game. So the relationship between these iterated functions that are unpredictable and the fractals that we looked at before is that the fractals are the graphical representation of parts of those chaotic functions like that. So in this case, I play the chaos game, and surprisingly, what comes out of it is the Sierpinski triangle. So, pretty surprising result, wouldn't you say, that playing that chaos game with just the points ends up giving us that Sierpinski triangle. So out of that complete randomness, that unpredictability of the chaos game, what we get is that very regular, self-similar fractal, the Sierpinski triangle. And again, this is one of the things that drew me to mathematics in the first place. When I would find things that seemed completely unrelated and then find out that there was a relationship between them, especially in this case right here, that's something I like about mathematics and kept me wanting to take more math classes. So I hope you enjoyed this video.